Take two. Today, nerds, we are going to start the last section of the chapter, and the last section of the chapter pulls it all together. Everything that we started learning last chapter in chapter 4, everything that we've done so far in this chapter, chapter 5, all comes together in this one big section. It's going to take me several days to teach it, like I said before I started the recording. What are we doing? The ultimate goal is to take polynomials of any degree we want and be able to graph them. That's the ultimate goal. And the only way that we can graph a polynomial is if we can factor a polynomial. And that's why we've been doing all the factoring so far. I do want to bring up something that we did yesterday right at the end, and I was kind of being chased by the bell, so I wanted to just one more time talk about the rational root theorem, the P over Q test as we call it, and what it does and why we do it. In order to factor a polynomial, you hope, fingers crossed, that it has some pretty factors, some pretty solutions. Pretty meaning either a whole number or something that can be written as a fraction. I know you don't like fractions, but whatever. They're considered pretty because they're not imaginary and they don't have radicals in them, okay? The only possible pretty solutions will be found by the rational root theorem. What you do is you list out all the positive and negative factors of the constant at the end. So it was 6. So we chose all the factors, plus or minus 1, plus or minus 2, plus or minus 3, plus or minus 6. These 8 numbers are all factors of 6. And you divide by the factors of the leading coefficient. Now you could say plus or minus 1, plus or minus 2, but the plus or minus would be redundant because you already have it on the top. So it's not that they don't go down there, it's just that why bother writing it in 2 different places? Okay, so just pick one and either do it on the top or do it on the bottom, it doesn't matter. Then you build out all the possible combinations of this fraction. So there are these 8 numbers, plus or minus 1 over 1, plus or minus 2 over 1, plus or minus 3 over 1, plus or minus 6 over 1. And there are also these 8. But some of those have already been said. So we've got plus or minus 1 over 2. But plus or minus 2 over 2, that's plus or minus 1. It's already written. We don't need to say it again. Plus or minus 3 over 2. Plus or minus 6 over 2. Oh, that's plus or minus 3. It's already written, so we don't need to say it again. Basically, these 1, 2, 3, 4, 5, 6, these 12 numbers are the only possible pretty solutions. And the reason why we want to find the possible pretty solutions is so that we could use the remainder theorem and start checking them one at a time. Literally guessing and checking them one at a time until we find, woohoo, a remainder of 0. Because after we start checking them all and we can start throwing away bad ones, we know they're not factors. But the moment we find one that has a remainder of 0, yay, you found a factor, and now you can do synthetic division, and you could take your polynomial and you could decrease its degree. And you would keep doing that until it got down to a degree that you could factor by hand or solve by hand if it didn't factor. And that is the whole point of the rational root theorem and the remainder theorem. It's so that I didn't have to tell you that x plus 1 was a factor. You would have just checked it. Because look, if I had chosen to do P over Q for this one, my options would have been plus or minus 1, plus or minus 2, plus or minus 4 over 1. So there were only 6 options that were pretty. So you would have started by plugging in 1 and hoping you got no remainder. And if you got no remainder, woot, then you would have done synthetic division. By the way, it would have worked. And then we could have plugged in negative 1, hoping we got no remainder. We already know that would have worked. We could have done synthetic division again. And we could have repeated that process, all these synthetic divisions, until we got to this quadratic that we found couldn't factor. If I asked you to solve for x, you could have. Look, positive 1, negative 1, positive 2, negative 2. And when a quadratic doesn't factor, how do we solve? Quadratic formula. You could have found all 6 solutions using the remainder theorem, the rational root theorem. Okay? But what if, what did I say, there's 12 numbers here? What if there was more? What if there was like 20 or 24 numbers? Like Jared just made a sneer. Like he's thinking that's way too much guess and check, right? There's got to be something that at least whittles the options down, right? Well, there is. And in today's lesson, after we've done these first two, I'll show you how to whittle it down. So we start with some fundamental connections and the fundamental theorem of algebra. Remember what I told you? It's all about graphing. We're all trying to get to graphing. But we can't get to graphing unless we can factor. So let's talk about some vocabulary. For any polynomial function and a real number k, real meaning not imaginary, all four of these statements are identical. And it's up to you to know that and understand what you're being told to do with certain words. If I tell you that x equals some number is a solution, that's the same thing as me saying x equals that number is a root. So the words solution and root mean the same thing for polynomials. It means it solves the equation polynomial equals 0. Remember I talked to you guys today about that. I said you can't solve a polynomial unless it's set equal to 0. So when you're solving, that means you set your polynomial equal to 0, and the answers you get are known as solutions, but they're also known as roots. They're also known as zeros. And the reason why we have another word for it is because it's literally where the polynomial would have equaled 0 if you had plugged that number in. So to say the word solution, the word root, or the word 0 all mean the same thing. So on your test, sometimes it's going to say solve for x. Sometimes it's going to say find the roots. Sometimes it's going to say find the zeros. And it will be on you to know that, well, that all means the same stuff. Okay? So it's just vocabulary. You have to know they all mean the same thing. Now, if k is a real number, that solution is an x-intercept of the graph of the function. So what happens if it's not a real number? It's still a solution, root, 0. All those three things still mean the same thing. It is still a solution. But if it's an imaginary number, it can't be an x-intercept because, well, the x-axis has only real numbers on it, right? So if you get an imaginary solution, an imaginary root, an imaginary 0, it is not an x-intercept. It basically tells you a place where your graph has a wiggle in it, but it didn't touch the x-axis with that wiggle. That's basically what it's telling you. And lastly, if you know k is a solution, then x minus k is a factor. We often find the factors and then use the factors to get our solutions. All of that means the same thing. And the fundamental theorem of algebra says the number of solutions, roots, zeros is equal to exactly the degree of the polynomial. So if you can remember all the way back to the very first lesson of last chapter, the first thing we did was in behavior. Remember that? And in order to pull off in behavior, we had to identify the degree of the polynomial. And then we had to talk about the coefficient, whether it was positive or negative. The degree of the polynomial tells you more than just what's going on with the endings. The degree of the polynomial tells you exactly how many solutions you have. Now, those solutions don't have to all be real. They could also be non-real. They could have I in them. But you'll have exactly that many solutions. And not only do they not have to be real, they don't have to be all different. They don't have to be unique. You can have repeated solutions. For example, I need a piece of scrap paper. You know what? I'll just draw it over here. I'm going to draw a quadratic real quick, whose vertex sits on the x-axis. How many solutions does that quadratic have? 1. A bunch of you said 1, and I saw someone held up a 1 finger. Max did. No, I'm sorry, you're wrong. All quadratics have 2 solutions. But you see, we're just splitting hairs. We're being picky here. The difference is the way we use the words. It has 1 unique solution, but it does have 2 solutions. It's just that that solution is repeated. Let's just say that was at x equals 1. Then the formula for this could have been y equals x minus 1's quantity squared. But you know that set of parentheses could have been written twice, right? That means there was actually two solutions. X equals 1 and x equals 1. They were just the same number. So not only do they not have to be real, they also don't have to all be different. They can repeat. And repeated roots will have a multiplicity, vocabulary word for you, that is greater than 1. Multiplicity is the number of times that a root is repeated. So here I would have said x equals 1 has a multiplicity of 2. It'll literally be the power of the factor. It'll be the exponent of the factor. So it's really just being picky about the words. This quadratic has one unique solution, but it does have two solutions because it has one repeated root. And roots repeat often. It happens. And that creates unique behaviors at those roots, those x-intercepts, which we'll get to later in the lesson, not today. Okay? I just need you to know the word multiplicity. It tells you that an answer is repeated. And whatever the exponent on the factor is, that's the multiplicity. In yesterday's work, none of these had exponents on the factor. That's an exponent within the factor. No exponents on the factor, no exponents on the factor. Basically, everything you saw yesterday was multiplicity of 1. Unique solutions. Today, when we find our solutions, we will identify where there's multiplicities. The first example says, state the number and type of roots. And that just means which ones are real, which ones are non-real, meaning you could say complex or imaginary, which ones are repeated, things like that, okay? Let's start with how many solutions this has. This is a 6-degree polynomial. So how many solutions does it have? 6 solutions. That doesn't mean all 6 solutions are different numbers, and that doesn't mean all 6 solutions are real numbers. It just means there will be 6 answers. Our job is to find them all, because it does say solve. It's already set equal to 0. So it says solve, we got to find them all. We solve polynomials by factoring. First job in factoring is GCF. This has one. What is it? What's the GCF? 2x squared. All right. Let's pop that 2x squared off of the front. When you undistribute that 2x squared, what you are going to get is an x to the 4th minus 16. Do you see what I see? Yes? Yeah, this is the difference of 2 squares. This is a special case. This is an a squared minus b squared situation. I hope that you're getting to a point in your skills where you don't have to write this formula every time you use it. A squared minus b squared should be free money. I'm not going to lie. I always write the cubic formulas when I need to use them, just like I always write the quadratic formula when I need to use it. But that's only because it's got a lot of moving parts. This is just conjugates. It's easy. So I don't want to have to write what x is, and I don't want to have to write what b is. You should be able to do that by now. What we have is 2x squared, and then the green thing will split into a pair of conjugates. I'll start writing the rest in black. X squared plus 4 and x squared minus 4. Special case. How many special cases are there in this line? Only one. Remember, a squared plus b squared will not factor. The word for will not factor is irreducible. So if you hear me say irreducible, that means I couldn't factor that number. I couldn't factor that polynomial. Irreducible means doesn't factor. This is irreducible, doesn't factor. But this does. Special case. That's another a squared minus b squared. again, I hope that you're recognizing them. And I hope that you don't have to write out what A and B are for the difference of two squares. Maybe the cubics. I mean, for the cubics, I would even write them down. But, you know. So I got this 2x squared that didn't change. I got this x squared plus 4 that's irreducible. I cannot factor it. But this will factor to x plus 2, x minus 2. McCutcheon in his Technicolor notes. There. We are fully factored. And now that it is factored, we can set each of the factors equal to 0 and get our solutions. Cool? Let's do the easy ones. Right here. What would make that equal 0? What would x have to be? X equals 0. Anytime you have an x outside of the factored parentheses, its solution is automatically 0. It's always 0. And it doesn't matter what numbers are out there with it. Its solution is x equals 0. But did you catch on to the fact that that x has a square on it? That means that answer is a repeated root. X equals 0 is the solution 2 times. It is repeated. With multiplicity of 2. So it accounts for 2 of our 6 solutions. There's 2 of them. X equals 0, oh, and x equals 0. Let's go for the next easy ones. These blue solutions are easy. What is this one's solution? Negative 2. And this one's solution? Positive 2. Those are just real roots, and clearly they're different numbers. The other 2, the last 2 solutions are going to come from x squared plus 4. So I need a little bit of space. I saved it over here. Let me go ahead and write it over here. I have x squared plus 4 set equal to 0, and we got to get x by itself. When a quadratic does not factor, it's either going to be one of these easy ones where you can get x alone quickly, or it's going to require the quadratic formula. Those are the only 2 options for irreducible quadratics. Either it'll be easy like this, or you'll have to use a quadratic formula. We're going to subtract 4 from both sides. And we're going to cancel that square with a square root. Talked about all this yesterday. So what does x equal there? Plus or minus 2i. A couple of you remembered. Anytime you cancel a square with a square root, you must have plus or minus. Remember I told you we were going to get 2 more solutions out of it. That's why it was 2. Because every quadratic will give you 2 solutions. And if it's irreducible, it's probably going to give you 2 imaginary solutions. It might give you 2 irrational solutions, but it doesn't matter. The point is, if it was an irreducible quadratic, it was going to produce a plus or minus situation, and you were going to get 2 answers. So those are your 6 answers. X equals 0 is twice, so it's a multiplicity of 2. X equals negative 2, x equals positive 2 could have been written as plus or minus 2. And x equals plus or minus 2i. And it's already written, but that x equals 0 is a repeated root. Would you like to ask me any questions about this? Again, the lesson is dense, and I need to make sure that you understand everything we're doing. Are you comfortable with the terminology? Are you comfortable with factoring, solving, do multiplicities worry you? Like, I just need to know, everything's good? Okay. All right. Then let's get some more examples under our belt. First of all, how many solutions will this have? There will be 3 solutions. This is a degree 3 polynomial. See, third degree polynomial. But those 3 solutions do not all have to be real or pretty or different. We just know there's 3 solutions. Let's tackle them. GCF, what is it? Negative 3x. Remember, when you're factoring something that begins with a negative, your GCF needs to be negative, so we have a GCF of negative 3x. And let's see what we get on the inside. It's going to give me an x squared minus 4x plus 5. Hey, look, a quadratic. At this point, we would be attempting to factor this quadratic. Are there 2 numbers that will multiply to positive 5 that add to negative 4? What numbers? Negative 5 and 1 multiplies to negative 5, though. Uh-oh. You see, if you say a positive number and a negative number, they're going to multiply to a negative number. The only way to multiply and get a positive is either both numbers are positive, which we know would add to a positive, or both numbers are negative. The only numbers that go into 5 are 1 and 5. And negative 1 plus negative 5 is negative 6, not negative 4. So guess what? This quadratic is irreducible. It doesn't factor. But we still need to solve. Okay, we've already talked about it. We're going to have to use the quadratic formula because that is irreducible. It does not factor. The quadratic formula will give us 2 solutions. It's going to give us 2 of our 3. The third solution comes from right there. What is the solution here? 0. We know x equals 0 because this x is outside the parentheses. In fact, I'm going to circle it to make sure I don't lose it as an answer. Remember, I told you students will often lose their GCFs. And the reason why they're important is because if they include an x, that's one of the solutions. Quadratic formula is one of those things that I never try to use without writing. So many places to goof it up. When you're doing your substitutions, please use parentheses. Please write the formula and then use parentheses when you're doing your substitutions. Because I don't want you to mess up the very first step, which is the negative 4. It goes wrong all the time. I think we talked about that earlier in the year when we were dealing with our quadratics. Yep, I never use the quadratic formula without writing it, and I always show my substitutions, even when it's just me working on my own. Negative 4 gives us positive 4, plus or minus. Negative 4 times negative 4 is positive 16. Negative 4 times 1 times 5 is negative 20. (16 minus 20), that's negative 4. What's the square root of negative 4? 2i. So we have x equals 4 plus or minus 2i over 2. And since both of these numbers can be divided by 2, we have to divide them both by 2. And look, we get our other 2 solutions. There's all 3 solutions. X equals 0, x equals 2 plus I, and x equals 2 minus I. There's all 3 solutions. You know what's interesting? In both examples, I ended up with an irreducible quadratic. Did the irreducible quadratic have to produce imaginary numbers? No. They could have produced irrational numbers like 1 plus or minus the square root of 3 or something like that. But either way, I would have had to use the quadratic formula, right? And how many solutions is the quadratic formula going to give us every single time? 2. What that does is it guarantees for us that our complex solutions will always come in pairs. And that is something that you must understand. It must make sense. Your quadratic solutions will always come in pairs. What kind of pairs? Conjugate pairs. Remember that just means the number in between them changes? Remember that from earlier in the year? Complex solutions will always come in conjugate pairs. So you can have 0 complex answers. You can have 2 complex answers. You can have 4 complex answers. You can have 6 complex answers. You cannot have 1, 3, 5 complex answers. That's impossible. Because the quadratic formula will always give you conjugate pairs. Okay? I think that orange pen is leaking. Look at my, just ink all over me all of a sudden. Okay, I'm going to put this orange pen off to the side. It's making a mess. Anybody in the room speak French? Anybody studying French? Nobody. Okay. This name is a French name. No, not oui oui. That's what the bathroom is for. This person's name is pronounced, no, Descartes. Descartes. Okay? No, it's Descartes. It's not Descartes. It's Descartes. Why make the name harder to say? It's Descartes. Okay. Anyway, Descartes was a very intelligent French mathematician. And he discovered and proved, I don't know if he discovered, I know he at least proved a pattern in solutions to polynomials that involved sign switching from term to term of the polynomial. This is called Descartes' rule of sign. And Descartes' rule of sign is used to find possible root combinations. The rational root theorem finds possible pretty solutions. Descartes' rule of sign finds possible combinations of solutions. All it does is take a list like this, and after we've found 1 or 2 solutions, it allows us to eliminate bad choices so we can guess and check less. So Jared's sneer won't have to be as large. But that's all it does. It literally just, it goes, hey, you found all the positive solutions that's going to have. Stop checking positive solutions. Something like that. It'll do those kinds of things for us. That's all it does. In itself, it doesn't find any solutions. It just tells us what combinations are possible. And this is going to take some paying attention to. And if you're not listening, you're going to be asking me a question that I've already answered and it's going to frustrate me. So please be paying close attention and listening. It's done in a 2 to 3 step process, however you want to think about it. I'm going to read it to you, and then I'll explain what it says. The number of positive real zeros, by the way, that doesn't mean they're pretty, it just means they're real and they're positive. The number of positive real zeros of a polynomial is the same or less than, which means less than or equal to, by an even number, 2, 4, 6, 8, as the number of changes in the sign of the coefficients. Okay, regular words. Regular words. You're going to look at your polynomial, and you're going to look from term to term, and you'll be looking for how many times the sign switched from plus to minus and minus to plus. You count that number up. Let's say the sign switched 4 times. That means your polynomial could have either 4 positive real solutions or 2 positive real solutions or no positive real solutions. Why was I decreasing by 2 each time? Because complex answers always come in pairs. That's why I'm decreasing by 2 each time. Because if there are complex solutions, there must have been either 2 of them or 4 of them or 6 of them. There could not be just one. Now, let's say you counted up your sign switches and there was only 3 sign switches. Then that would mean there could be 3 positive real answers or 1, I had to be careful which finger I showed, positive real answer. Again, I'm subtracting by 2 because I'm allowing for the complex ones to show up in pairs. Okay? The next step is, and this is the one you're really not going to like, now you have to plug in negative x and get the new function. Count the sign switches again. This one would tell you the number of possible negative real solutions. And by the way, there will always be the degree of the polynomial number of solutions. So you have to make sure that the number of solutions always adds up to the degree of the polynomial. So if the positives and the negatives didn't get you enough, that means the rest of them were complex. Now, it's tough to figure out what all that means in words. It's much better to just do some examples. Okay? So let's do an example. First, we look at f of x to figure out our positives. So this is us working out the number of possible positive real solutions. For this one, you change nothing. And then you identify the number of times you saw the symbol change from positive to negative or negative to positive. How many times do you see that happening in this polynomial? 1 time. I see it happening 1 time, and it's occurring from here to here. So it's occurring 1 time. I can't subtract 2 from this 1 time because this 1 time is telling me that there's that tells me that there is 1 positive real solution. If I try to subtract 2 from that, I'd be getting the number -1. And how are you going to have a negative number of solutions? That doesn't make any sense. Okay? Now let's go to the negative case. This one requires us to plug in negative x and see what happens. And you will have to clean it up. The good news is that's not hard to do. Every time there was an even exponent, you're just going to ignore the fact that you plugged in a negative number because an even number of negatives is positive. And every time there was an odd exponent, well, the symbol's going to change from what it used to be. So this is going to give me 4x to the 4th because that'll be positive. But this will give me negative 2x to the 3rd because if I raise this to the 3rd power, I get a negative number. Negative negative is positive, and then -1. And now we count the sign switches. How many sign switches do you see in this one? Positive to negative, negative to positive, positive to negative. There are 3 of them. And since that number is large enough, then I know there could be 3 negative real solutions, or there could be 1 negative real solution. And now we list out what the possible combinations are. And remember, the complex just makes sure that we add up to the right number. Wait a minute. How many solutions do we know this polynomial has? There are 4 solutions to be guaranteed. 4 solutions are guaranteed. Okay. I know that there are either 3 or 1 negative solutions. They don't have to be pretty. But there's either 3 of them or there's 1 of them. We said there was 1 positive. So there's either 1 positive and 3 negatives. That would be all 4 solutions, right? So if I had 1 positive and 3 negatives, how many complex solutions are left? 0, because it already adds up to 4. But this is possible combinations. And I can't subtract 2 from this number. That guarantees to me that my graph will cross the x-axis one time on the positive side. It's guaranteed because I couldn't subtract 2 from it. So if there was 1 positive and 1 negative, how many complex would there have to be? So all this does for us is tell us, and by the way, this is what I wanted. This is the answer to this question. These are the possible combinations. This is telling me my graph either crosses the x-axis 3 times on the negative side and 1 time on the positive side, or crosses the x-axis 1 time on the negative side and 1 time on the positive side. And then somewhere else there is a wiggle in the graph that didn't touch the x-axis. So it's either this solution, this setup, or this setup. That's all we know. Now, if we were trying to do the rational root theorem to figure out what the possible pretty answers are, if let's say I wanted to try to factor this thing by hand, it would be plus or minus 1 over plus or minus 1, or say let's plus or minus 1 over 1, or plus or minus 1 over 2, or plus or minus 1 over 4. But that is if I wanted to factor it. For now, I just wanted to be able to figure out what all of the possible combinations were. Okay? Here's what I want to do. And period 1 didn't get to see this. I want to go back to this one. Not that one. And I want to say, yeah, we'll just talk about it. You would not attempt to use Descartes' rule of sign on this. And the reason why is because it has a GCF of x. Because x is part of its GCF, you would not use Descartes' rule of sign on it. Because that solution is 0. And 0 is neither positive nor negative. So if you're dealing with a polynomial that has a GCF of x, you need to pull that x away first. And then you can use Descartes' rule of sign on what remains. Okay? So just be careful about it. I want to look at this one real fast, again from yesterday. Let's use Descartes' rule of sign on it real quick. How many sign changes do we see on f of x? I only see 1. So for the positives, we know there's 1. But if you were going to find f of negative x, everybody's packing up like I'm done. It's crazy. You can actually hear the people that don't want a's. Everywhere that there's an odd exponent, I told you the sign would change. So you would get a negative 2x to the third. 4x squared would be unaffected. Plus 5x minus 6. And if you counted these sign changes, there's 1 and there's 1. So for the negatives, there's either 2 or there's 0. I've already been guaranteed that there's a positive one. This is a degree 3 polynomial. So if there were 1 positive and 2 negatives, how many complex would be left? 0 of them. This is a degree 3 polynomial. If there's one positive and no negatives, then how many complex are there? 2. And the reason why this is useful to us is you know there's only one positive real root. And let's see, you're going through your guessing and checking. The moment you found a positive that works, you know it's the only positive that works, and you could stop checking all the other positives. They are now impossible. It literally just like cuts the guessing and checking down in time. That's all it does for you. But that is useful in case there's dozens of options. I just wanted you to see it. We'll practice more Descartes' rule of sign tomorrow and actually using it.